The Andromeda Galaxy played a pivotal role in reshaping our understanding of the universe and our place within it. Our galaxy, for example, is the Milky Way, and the nearest galaxy to us is the Andromeda Galaxy. We think there are about 100 billion galaxies in the visible universe. It served as compelling evidence that the cosmos and the concept of creation don't revolve around Earth. This discovery shattered the notion that the Milky Way was the sole galaxy in existence, suggesting that we are just a tiny part of the vast universe. While we have accumulated knowledge about Andromeda over the last century, much of it was gathered from observations made on Earth. However, with advanced tools like the James Webb Space Telescope now at our disposal, our perspective has drastically changed. Surprisingly, the recent data obtained from the James Webb Space Telescope has upended our previous notions about the Andromeda Galaxy. Another cosmic puzzle needs to be solved. The JWST has received signals from our neighboring galaxy, leaving the entire scientific community astonished. Join us as we explore how the JWST received an alarming signal from our neighbor, the Andromeda Galaxy. Indeed, the perception of the Milky Way has undergone significant changes over the course of human history, shaped by our evolving understanding of the cosmos. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and mythologies. It was often seen as a mystical and central element in the cosmological beliefs of different cultures. As our scientific knowledge advanced, particularly with the development of telescopes and the work of astronomers like Galileo Galilei, we began to realize that the Milky Way was not just a celestial concept but a vast collection of stars, planets, and other celestial objects. This realization revolutionized our understanding of our place in the universe. Today, thanks to modern telescopes and astronomical research, we have a much clearer picture of the Milky Way as a barred spiral galaxy containing billions of stars, including our own sun. In the 1920s, Edwin Hubble, an American astronomer, made a transformative discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble observed distant nebulae beyond the Milky Way. Through the observations and analysis of these objects, he showed that they weren't actually part of the Milky Way but were entirely separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. The Andromeda Galaxy has a rich history of observations that dates back centuries. One of the earliest known records of the celestial object can be traced back to the 10th century, when the Persian astronomer Abdul Rahman al-Sufi described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that al-Sufi was able to identify this distant cosmic entity without the help of telescopic instruments, relying solely on his keen eyesight and observations. It wasn't until 1612 that a detailed description of the Andromeda Galaxy, based on telescopic observations, was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive cosmic structure. Later, in 1764, the renowned French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his well-known Messier catalogue, mistakenly attributing its discovery to Simon Marius. However, that doesn't diminish Messier's role in putting Andromeda on the map. For almost 100 years after these observations, astronomers worldwide sought to understand more about this mysterious galaxy, each adding to the last one's findings. Before that, Galileo Galilei, an Italian astronomer, revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking observations that challenged the prevailing Aristotelian cosmology. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, an original theory or new hypothesis of the universe. According to Wright's speculation, the Milky Way was not a random distribution of stars in space but a completely flat layer of stars. He also suggested that a portion of this vast structure was our own solar system. While Wright's hypothesis was a step forward in understanding the structure of the Milky Way, it was still limited by the observational technology available at that time. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when the English astronomer William Huggins made a groundbreaking observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical gaseous nebula. This observation paved the way for the world to understand Andromeda for what it really is. The Andromeda Galaxy has a mass estimated to be between 1 and 2 trillion times that of our Sun, making it a colossal cosmic structure that just happens to live relatively close to us in the vastness of space. In all the research conducted until now, scientists believe that Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. One intriguing aspect of Andromeda's origin is the hypothesis that it came into being through the merging of several smaller protogalaxies. This suggests that over billions of years, smaller galactic entities gradually came together under the force of gravity to form the majestic Andromeda Galaxy we see today. Galactic mergers are common occurrences in the cosmos, shaping the growth and structure of galaxies. However, for a long time, astronomers thought Andromeda was significantly more massive than our own Milky Way galaxy. This misconception is understandable considering the limitations of the observational tools available in the 1700s and 1800s. Recent research has brought about a reevaluation of these beliefs. New findings have led scientists to somewhat reduce their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. The current understanding is that the masses of these two cosmic giants are much closer than previously thought. So if you were on Andromeda and looked at Earth, you'd see just as massive of a galaxy. This puts into perspective how colossal the Milky Way itself is too. The Andromeda Galaxy's physical dimensions, though, are what astronomers totally agree on. It's known to stretch farther than our own Milky Way, with an impressive diameter of about 220,000 light-years. Andromeda surpasses the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years, making it a truly significant cosmic entity taking over a large region in space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. In the heart of the Andromeda Galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow elliptical paths similar to planets orbiting the Sun in our solar system. At a certain point in their elliptical orbits, stars come closest to the black hole, and this point is called the perihelion. At the perihelion, the gravitational forces are at the strongest they can ever be, causing the stars to move at their highest speeds. This is when the stars bunch up and become more concentrated in space around the black hole. As they bunch up, the stars release energy in the form of radiation, including visible light and other types of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galactic core of Andromeda's active galactic nucleus, AGN. More on this later. This distinctive feature provides valuable clues about the gravitational dynamics and interactions between the supermassive black hole and the surrounding stars. To understand this better, let's take a look at what an AGN is. The active galactic nucleus, popularly known as AGN, is a highly energetic region at the center of a galaxy. It is characterized by intense emissions across various wavelengths, from radio waves to X-rays. AGN are powered by the presence of a supermassive black hole at the heart of the galaxy. These supermassive black holes are incredibly dense regions in space where an enormous amount of mass is concentrated within a very small volume. When astronomers observe the active galactic nucleus using advanced telescopes like the Hubble Space Telescope, they notice a very interesting phenomenon. One of the most fascinating features of the Andromeda Galaxy is its AGN. It appears to have 2 points of concentration, meaning there are 2 distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding areas. The brighter concentration is the second point of focus, which is just slightly off the true galactic center. Within this area lies the supermassive black hole. The mass of this black hole has been estimated to be between 1.1 to 2.3 million times that of our Sun, which means it weighs approximately 110 to 230 million times as much as our Sun's supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and they play a crucial role in the evolution and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various wavelengths, which is why the AGN is highly luminous. When astronomers observe the active galactic nucleus of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature is a result of the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda Galaxy also has another super interesting feature: an abundance of globular clusters. These globular clusters are tight groups of stars that orbit around the center of the galaxy, kind of like satellites around a planet. The Andromeda Galaxy is known to contain more than 500 globular clusters, which is significantly more than the number found in our Milky Way. These clusters are believed to be among the oldest known objects in the universe, having formed billions of years ago. Studying globular clusters in Andromeda and other galaxies provides valuable insights into the formation and evolution of galaxies over cosmic time. In recent years, the Andromeda Galaxy has played a central role in advancing our understanding of the cosmos. The James Webb Space Telescope has already had a significant impact on our understanding of the universe's formation and evolution, including the discovery of the first stars and galaxies that formed after the Big Bang. The Andromeda Galaxy, also known as M31, continues to captivate astronomers and enthusiasts alike with its vast cosmic mysteries and profound implications for our understanding of the universe. Its sheer size and proximity provide a unique opportunity for detailed study, offering insights into galactic evolution, structure, and dynamics that extend beyond our own Milky Way. One of the enduring questions surrounding Andromeda is its future interaction with our galaxy. Current models predict that Andromeda and the Milky Way are on a collision course, set to merge in about 4.5 billion years. This cosmic event, dubbed the galactic collision, will reshape both galaxies dramatically. Despite the immense scales involved, such collisions are not uncommon in the universe and play a crucial role in shaping the evolution of galaxies. Observations of Andromeda have revealed a complex interplay of stars, gas, and dark matter within its structure. Dark matter, an elusive substance that does not emit, absorb, or reflect light, comprises a significant portion of the galaxy's mass. Its gravitational influence shapes the orbits of stars and helps stabilize the galactic disk over billions of years. Understanding the distribution and behavior of dark matter in Andromeda provides vital clues about its formation and evolution. In addition to its structural features, Andromeda's stellar population offers insights into the history of star formation and evolution. The galaxy hosts a diverse array of stars, from young, massive stars illuminating regions of intense star formation to older, cooler stars that have evolved through various stages of their life cycles. Studying these stellar populations helps astronomers reconstruct the galaxy's past and trace the conditions that led to its current state. Recent advancements in observational techniques have enabled astronomers to probe deeper into Andromeda's core and outer regions, unveiling previously unseen details. High-resolution imaging and spectroscopic analysis reveal intricate structures such as stellar streams, globular clusters, and faint dwarf galaxies orbiting Andromeda. These discoveries challenge existing models and refine our understanding of how galaxies grow and interact over cosmic time. The study of active galactic nuclei (AGN) within Andromeda provides another avenue for exploration. These highly energetic regions, powered by supermassive black holes at the galaxy's center, emit intense radiation across the electromagnetic spectrum. By analyzing AGN emissions, astronomers gain insights into the feeding mechanisms of black holes and their impact on galactic evolution. Andromeda's AGN exhibit unique characteristics that offer comparative studies with similar phenomena in other galaxies. Moreover, Andromeda's environment offers a glimpse into the broader cosmic web of galaxies and their interconnectedness through gravitational interactions. As one of the largest members of the local group of galaxies, which includes the Milky Way and dozens of smaller galaxies, Andromeda's gravitational influence extends over vast distances. Interactions with neighboring galaxies shape its morphology and contribute to the ongoing evolution of the galactic ecosystem. Technological advancements continue to revolutionize our ability to study Andromeda and galaxies beyond. The upcoming generation of telescopes, such as the Nancy Grace Roman Space Telescope and next-generation ground-based observatories, promise unprecedented views of Andromeda's stellar populations, dark matter distribution, and galactic dynamics. These instruments will further refine our understanding of galactic processes and shed light on fundamental questions about the universe's origins and evolution. Beyond its scientific significance, Andromeda holds a cultural and inspirational allure for humanity. Its depiction in art, literature, and popular culture reflects our fascination with the cosmos and our place within it. From ancient astronomers who marveled at its faint glow to modern-day scientists unraveling its cosmic secrets, Andromeda continues to inspire wonder and curiosity across generations. In conclusion, Andromeda stands as a beacon of exploration and discovery in the realm of astronomy. Its study illuminates fundamental aspects of galactic evolution, dark matter dynamics, stellar formation, and the interconnectedness of galaxies within the cosmic web. As our technological capabilities expand and our understanding deepens, Andromeda will undoubtedly reveal more about the universe's past, present, and future, reinforcing its status as a cornerstone of astronomical research and human exploration.